Okay, this video is about doing calculations for electromagnetic radiation. And electromagnetic radiation is radiant energy. And we have different regions of radiant energy like light or infrared radiation or ultraviolet radiation or X-rays or radio waves. And I'm going to do a calculation on visible light. And it has a wavelength, lambda is wavelength, of 725 nanometers. Now, we use wavelength and frequency to describe electromagnetic radiation because it propagates as a wave, and we know the distance from peak to peak is the wavelength, and that's a length, so it's in meters. And then frequency, as these wavelengths propagate through space, they pass a fixed point, and the number of times they pass that fixed point we say is frequency. And so it has a unit of 1/seconds, or sometimes people write hertz. All right? And again, these numbers often have prefixes in them. They're in scientific notation, so sometimes they give students trouble with calculations. So what we're going to first do is we're going to first calculate the frequency, and frequency has that symbol, looks like a V, a nu, and wavelength lambda. Now, before we can plug it in this, we have to know a couple constants. The first one we have to know is the speed of light, 3.00 times 10 to the 8th meters per second. That's pretty fast. So we're going to plug this into this equation because we want to know the frequency. We ultimately want to know how much energy that photon, that single little packet wavelength of light, is actually carrying. So we're going to first take, and I'm going to just replace this. I'm going to say this is 725 times 10 to the negative 9th meters, because I can replace that nano with times 10 to the negative 9th. That's going to come over here, and when I plug in the speed of light, and I'm going to keep my units, and my wavelength, 725 times 10 to the negative 9th meters, really all I have to do now is divide both sides by this 725 times 10 to the negative 9th meters. It will cancel out on that side, the meters will cancel, and I'll be left with the frequency, which is, the frequency is equal to 4.14 times 10 to the 14th, and what's left is 1/seconds, or hertz. That's the same as 4.14 times 10 to the 14th hertz. Now, both those things represent the same red light. I could represent it as 725 nanometers, or I could say it's the same as 4.14 times 10 to the 14th reciprocal seconds, or hertz. Now, once you have hertz, you can plug that in to this equation. This energy equals n is the number of photons. So how many of these smallest packets of light are there, times a constant, which I've written down here, Planck's constant, times the frequency. So I only want to know one photon. If I was being asked for a mole of photons, I'd put 6.02 times 10 to the 23rd here. It would be a counted number, or a dozen would be 12. I'm going to put 6.63 times 10 to the negative 34th joule seconds. And then I'm going to put my number here, times 4.14 times 10 to the 14th reciprocal seconds. And now you'll notice the seconds cancel, and exactly what I'd expect, my energy is now equal to 2.75 times 10 to the negative 19th joules. That's a teeny number, but it's a single photon of light, and so it's not going to be a lot. If you were calculating the energy of a mole of photons, this would be a bigger number in joules or kilojoules that we could think of. So when you're thinking of electromagnetic radiation, two characteristics, wavelength and frequency. They're just a different way of looking at the same thing. And then when we want to know how much energy, because it is radiant energy, we can plug it into this equation right here. The number of photons, more energy, times the constant, and it's directly related to the frequency of that photon or light.